Let's get back to talking about decision making. All right. So it seems like at this point in your lives, you've all made lots of decisions, some of which are probably bad decisions, most of which are hopefully good decisions. But of course, no one's going to tell you, right? This is a good choice, this is a bad choice. It's never that clear, right? So in real life, you could have lots and lots of decision making trees that we're all kind of constantly drawing, right? You might start with a couple of options, but each option might then lead to more possible options, and the alternate option that you didn't take might also have had lots of different options. So it ends up being a pretty complex tree diagram of possible decisions. And maybe at some point you might just throw caution to the wind and just say there's a lot of tough decisions ahead, and so we'll just kind of roll with it and see how it goes. But the study of how we make decisions and how we make calculated decisions in contrast to not so calculated, maybe emotional decisions, is the study of neuroeconomics. Right? So this is a really burgeoning field, right? So it's a combination of neurobiological studies and more computational studies on how we make decisions, and it's based fundamentally on the value that you can gain out of certain decisions. And it's, of course, inspired by some classic studies from economics, or some economic models of rational behavior. But it's not just about economic models. There's also, and it's not just about rational behavior, there's also deviations from rational behavior, which turn out to be psychologically useful and maybe even protective. And of course, when you think about economics, you think that it's mostly about money, but it turns out to be not just about money. It turns out to also be about how we relate to other people. Right? So there's some value to objects and to interpersonal interactions. Right? So things like fairness, or how do you establish that a person that you're interacting with is acting fair? Right? Things like trust, right? How do you learn to trust somebody? Right? So it turns out that is also a study, a question that can be has been looked at by people with a neuroeconomics approach, and so it comes down to decision making essentially. And as I said, there's not just cognitive components that are at play in decision making, but emotion kind of interacts with cognition, and that is that interaction is kind of the crux of what we'll talk about. So a little bit about what the lesson of decision making will be about. Right? So we'll start by talking about the circuitry, so the anatomical networks and areas that are important for giving rise to our motivation and reward. And by the way, if you're very interested in these topics, motivation and reward, Professor Mike Robinson teaches a course on motivation and reward, which is very good. So you might find that to be interesting as well for future reference. Then there's also more from a computational perspective, a mathematical perspective. What are rational decisions, right? What are rational choice models? How do you make a rational decision that just maximizes value to yourself? And having said that, how do you deviate, and when do you deviate from those rational choices? And then there's a really important model that turns out to be kind of a guiding principle for how we think about decision making, and that's the reward prediction error. And that's so we'll spend quite a lot of time talking about that, both from a mathematical perspective and from neurobiology, or recording from neurons while people are doing certain reward predictions and so on. And there's an important role of uncertainty. Right? So obviously, the reason why a lot of decision making is hard is that you don't know all the options. Right? So there's a lot of uncertainty in your outcome, and then there's also a lot of uncertainty just because things change as a result of your actions. Right? So if you've chosen to do something, you can't unchoose it and do the other thing. Right? So there's kind of a fictive reward, or an imagined alternative scenario that's part of uncertainty in decision making. And then the last part of the talk about decision making will be about two-person or multiple person decisions. So when you're making a decision for someone or making a decision jointly with someone, how does that affect your decision alone? So I think we obviously won't finish talking about decision making today, but I hope to get through the part on motivation and reward circuitry. Okay, and the general story is that there are multiple neurotransmitters that are involved in your in your brain, but most importantly, the dopaminergic connections are the primary connections that give rise to motivation and reward. Right? So these are just a few connections, a few of these neurotransmitter pathways in the brain. Right? So we know that there's dopamine as well as a major neurotransmitter. There's also glutamine, that's a very important one, and then GABA is another one. But the reason why I'm showing you this is to highlight the green stuff, or the green pathways, which are the dopaminergic pathways in the brain. And so that's the primary reward circuit that's important for coding for motivation and reward. So the major areas in play that are dopaminergic, part of the dopaminergic system, include the ventral tegmental area, which is in the midbrain. And so recall very, very early on in this course, when we were doing neuroanatomy, there was one slide where I said that the midbrain and the brainstem are important for homeostatic functions, and they also include the ventral tegmental area, which is in the midbrain, which is important for reward functions. And so that's where it comes back to play an important role in what we're talking about when it comes to decision making. Then the ventral tegmental area then has synapses towards the nucleus accumbens, NAC, and the nucleus accumbens. And this is the rat brain, right? So this is just an example of how these systems are laid out in the rat brain. And in the next slide, I'll show you how it translates in the human brain. So the nucleus accumbens is a major seat of dopaminergic activity. And then these areas then project to the medial prefrontal cortex, which is tiny in rats, but it's much bigger in humans. Right? So this is the human dopaminergic system. And so I'll start out by pointing out the areas that I've already talked about. So the ventral tegmental area, so that's in the midbrain. And then the nucleus accumbens, which is right here, it's kind of just on the gateway towards the frontal lobe, right? Kind of sitting in between the striatum, this part of the striatum, and the frontal lobe. So that's a very important hub. And then also the medial prefrontal cortex, especially the ventral medial prefrontal cortex. The other point to note about dopaminergic pathways is that there's not just one pathway. There are several sub-pathways that are part of the dopaminergic system. And so the areas that we've talked about are the mesolimbic and mesocortical pathway. Right? So that means that there are connections that terminate in the limbic system. Right? So that's around the thalamus, and also that terminate in the cortex, especially in the medial prefrontal cortex. But another part of this pathway is the nigrostriatal pathway, and that also starts from the ventral tegmental area and substantia nigra, which are very close together in the human brain. But then they also terminate towards areas such as the motor cortex. And so the nigrostriatal pathway is very important for cortical control of motor behavior. So the really important. So one group of patients, for instance, who have trouble with in the nigrostriatal pathway are people with Parkinson's disease. And so we'll talk about how that pathway, which is disrupted in people with Parkinson's disease, then affects the rest of the behavior that is subserved by the dopaminergic system, such as gambling and impulsive decision making. So this is just another view of the dopaminergic pathway. So it has this mesolimbic pathway that goes from the ventral tegmental area towards the nucleus accumbens. Then there's a mesocortical pathway. So the textbook talks about mesolimbic and mesocortical as one overall circuit. And I think that's fine. The mesocortical pathway then goes towards the cortex, especially the frontal lobe. And then nigrostriatal pathway goes towards the more areas that are more important for motor control. Okay, so when we're talking about the nigrostriatal pathway, right, so I said that the substantia nigra and the ventral tegmental area are quite close together in the midbrain. But what the nigrostriatal pathway does is it terminates it has some terminations in the striatum. So what exactly do we mean when we're talking about striatum? Well, it's the same as the basal ganglia. Right? So when people who are studying the motor control, they're talking about basal ganglia. That's analogous to what people who study motivation and reward talk about when they say striatum. So so we know from previous days that basal ganglia includes the nucleus accumbens and the putamen and the caudate, and the globus pallidus. And so people who talk about this as the striatum, they also talk about dorsal striatum versus ventral striatum. And so dorsal striatum generally refers to the caudate, right, which is just immediately ventral to the ventricles. And so this is right here, it's the caudate. And then ventral striatum includes the other areas of the basal ganglia, especially nucleus accumbens and putamen and globus pallidus. So this is it's especially dark on the screen. I don't know if there's much we could do. It's okay. But so this is just a slice, coronal slice that shows you the dorsal and ventral striatum, and on the top we have the three-dimensional reconstruction. So so imagine if the brain is looking in that direction, right? So that you can think about these subcortical structures as the three-dimensional gray matter structures that can get, and so that's just the three-dimensional reconstruction of those structures. Okay. So to show you a little bit more about how exactly the areas in the nucleus accumbens and the striatum connect to other areas of the brain. Right, this is quite a clear example of diffusion tensor imaging study that took the seed region in the nucleus accumbens. Right? So again, dorsal striatum, ventral striatum. Right? So they're taking areas from the nucleus accumbens, which is part of the ventral striatum, and just finding connections all over the brain. And when you do that, the majority of the connections go towards the frontal lobe, especially the medial prefrontal cortex. Okay? And so this just shows you how anatomically these areas are connected. And so the nucleus accumbens is actually, in rats, is quite similar to what they would call the septal area. So this is a kind of an older term, but it's essentially what corresponds to what we think of as the nucleus accumbens in the human brain now. And this is a classic study from the 50s where Olton Milner, they took rats and they actually electrically stimulated their nucleus accumbens. But they rigged it in such a way that the rats would have to press a lever to get this electrical stimulation to the septal area. And when they did that, they found that the rats were really, really into pressing that lever to give themselves that brain stimulation. So much so that they stopped doing anything else. They stopped eating, they stopped sleeping, they stopped doing any of their regulatory functions. They would self-stimulate to the point of death. So this is actually a really remarkable and striking behavior, right? So it's essentially mimicking a kind of addictive behavior, right? So these rats, once they were given the opportunity to self-stimulate in these dopaminergic rich areas, they would essentially stop regulating their behavior and only care about stimulating their dopaminergic system. So now we know that the septal area, the nucleus accumbens, has a really important role in motivation and reward, and that the rats certainly want stimulation in those areas. But we also, it turns out that wanting and liking are not necessarily the same thing. And this is a distinction that I think is very clear from if you take the course on motivation and reward. It's a really important distinction. And this part of this comes from another classic study in 1998. So Berich and Robinson, not our Professor Robinson. There turns out to be a different Robinson who worked with the same Berich that our Professor Robinson also worked with. It's a small world. But anyway, so what they did was these studies that involve depleting dopaminergic areas in rats. Right? So what they did was they injected some neurotoxin called OHDA, which affects the dopaminergic system selectively. And so this is just showing that the neurotoxin worked. Right? So after the nucleus accumbens activity was depleted in these neurotoxin-treated rats compared to controls. And then what they did was they measured how much the rats ate, right? So, but they also measured their responses. And so, really useful set of behaviors that the rat researchers could look at was their facial responses of the rats to food. Right? So if you give them sucrose, which is just sweet water, right, sugary water, the rats would of course take in a lot of the sugary water, and then they would also lick their lips and make facial expressions that look like they're enjoying themselves. In contrast, of course, if you give them quinine, which is bitter, they would, of course, not drink the quinine solution, but they would also make these aversive behaviors, or so kind of make these disgust-looking faces that suggest that they are averse to that stimulus. And the really striking finding from Berich and Robinson was that when you give rats, the neurotoxin-treated rats, quinine and sucrose, they no longer drank the sucrose water, but these aversive and hedonic reactions remain. So even though they are no longer interested in taking more sucrose and less quinine, when you gave them those different solutions, they still made these facial expressions of hedonic or pleasurable responses in response to sucrose, and aversive responses or disgust faces in response to quinine. So this really tells us that wanting and liking are not necessarily the same thing. Right? So what dopamine is especially important in is the seeking behavior and wanting the stimuli, and not necessarily liking. And so, so this is an overall model of what Berich and Robinson did. Right? So once you have this OHDA lesion, right, you're lesioning the dopaminergic system, and this eliminates the wanting part of the model, while the liking part of the model was still intact. Right? And so you can think about how this differentiation between wanting and liking is extremely important for regulating people who have addictions, right? And so if you could imagine if you're addicted to something, even if you don't particularly like it, you still want it and you'd still seek it out. And that's because there's a variety of different drives that work, right? So there's the reward incentive itself, right? And then there's the drive towards that reward, and there's some top-down control that might be regulating that reward and drive balance. And when the top-down control is diminished, right, such as in people who are affected by addictions, then that reward salience cue becomes especially large, and then that drives your behavior in a way that you would normally be able to control if you were not addicted. So drug addiction is a really classic example of this. Another example is people who are compulsively gambling, right? So in gambling, there's this really neat work from lab studies on gambling, and so we don't actually have people gambling in a casino in the lab, but you could come up with these slot machine type things that you could give to people in the lab, and you could have people playing slot machines. And so you guys know how slot machines work, right? One-armed bandits, right? You can you press the slot, you put the money in, right, and then you pull the arm, right? You trigger the thing to happen, and then these like pictures kind of rotate, right? And if the pictures align, right, you get 2 or 3 of the same pictures aligning with each other, then that's a win, right? And so what you could do make a situation where you can get a near miss. Right? So these two rows of pictures are almost aligned. Right? So you didn't quite win, but you almost won. Right? So there's a no-win situation, but it's a near-miss situation. And so when you rate your chances of winning, you could have people do. This is a really fun finding. You could ask people to play these games, and you can ask people to rate your chances of winning. And you can either have the participants actually pull the one-armed bandit, or actually control the slot machine. And when the participants controlling the slot machine, and you get this kind of near-miss situation, you will say, "Oh, I'm very close to winning." Right? So you have a positive chance of being close to winning. In contrast, when you have a computer, right, so you could have someone in the lab and you can say, "Oh, the computer's just going to play this game for you," and afterwards you could say, "How would you rate your chances of winning?" And in response to the computer control situation, people say that, well, the game is rigged against you, so they think it's not. They're not more likely to win. And it's what's quite interesting is that when you have these near-miss situations that are controlled by the participant will then keep saying that they want to play more. Right? They keep wanting to continue to play the game, whereas with the full miss situation, so if these were not so close at all, the participants would not be as interested in playing the game. But generally, what we're seeing in response to gambling outcomes, when you have all winning outcomes compared to non-winning outcomes, you see activity in the ventral striatum substantia nigra, and then also in the ventral striatum. So you can see how all the areas that we just talked about as being an important part of the dopaminergic system are generally active in response to winning outcomes, right, when you've won the gamble, versus no-win outcomes. However, what's even more interesting is that when you compare the near-miss outcomes minus the full-miss outcomes, right, so this is when you almost won, right, when the two pictures almost align, so that's the near-miss, and you actually won $0, right? So monetarily, you're not actually getting more rewarded, but it turns out that the near-miss responses still results in striatum activity in response to almost winning compared to not winning. And so this is quite interesting because this is, again, the incentive cue is quite dissociated from the reward itself, right? Because you're still not making any money from a near-miss outcome. And then another piece of evidence that the ventral striatum is a really important part of motivation and reward comes from people with Parkinson's disease. It turns out that people with Parkinson's disease, some of them will take drugs such as L-DOPA. That's a very common drug for treating people with Parkinson's disease, and it can be quite effective at eliminating or diminishing the presence of symptoms, motor symptoms in people with Parkinson's. And what they found was that when these patients were on were on a dopamine agonist, such as L-DOPA, what they did was they ended up showing a lot of compulsive gambling behavior. So before L-DOPA treatment, most patients would be very rare gamblers, if at all. But as long as they were on these dopamine agonists, as long as they were on the dopaminergic drugs, they became much more active gamblers. And then as soon as they got off of the dopamine agonists, right, once they were no longer taking those drugs, they ended up not gambling again. So there's plenty of evidence of Parkinson's patients taking dopamine and that leading to changes in their gambling behavior. And so a couple of newer lines of work looking at particularly at gambling behavior and also at your rewards incentive and the salient structure of different cues. There are some researchers and also some businesses now that are kind of marketed as neuromarketing which is the goal of understanding unconscious thoughts and implicit attitudes to stimuli. And this can be not just sensory and cognitive, but also your affective responses to stimuli. And so I know some people who are doing this. I mean, it can be a little bit sketchy, but you can think about how being able to predict your dopaminergic rewards in response to certain stimuli might help you predict consumer behavior, right? And it might help you, for instance, identify ads that might be more effective than others. And so a pretty good example of this is like Coke versus Pepsi, right? So they're somewhat similar sweet beverages, but of course the brand matters a lot. And what this particular study is showing is that whenever among people who prefer one versus the other, such as Coke versus Pepsi, in response to the familiar brand, or just the brand alone, tends to increase your activity in areas that are important in the dopaminergic system, such as the ventral medial prefrontal cortex. So I think I'll stop there, except just I think this is just a really lovely, lovely picture. Neuroscientist Ryan Gosling.tumblr.com. Yeah. So does he want the girl, or does he just like the girl? Okay. See you guys next time.